Okay, hi everyone. So, my name is Jeff. I don't know if, I introduced myself Monday. So in this lecture, it's going to be a bit more about dynamics, on top of the complexity of network that Jim was talking about. And so, I don't know if it's going to be math intensive or not. It depends a bit on everyone's background, but the idea is to kind of build. Like, I'm going to start off with like general introduction about like historical and intuitive ideas of ecology, and then the goal will be to build a bit a mathematical metaphor or some form of a mathematical object that will encompass some of the like essential ideas that we will have in mind from the intro, and see where that leads us in terms of insights. And then I'll also point at some new like some perspective, and we'll see how far we go. I don't need to go all the way, and you should definitely like interrupt me for questions. Like I have no interest in talking into the void. So if you don't understand what I'm saying, you should ask me. It'll be fine. Okay, so some a bit of intro, a bit redundant with, of course, with what's been said this morning, but there's this idea of when we do ecology that it's a science that has to embrace some form of complexity in various forms. But if we start really slow, so clearly what we can, if we look around us, we see nature is complex. There's many different entities and they interact with one another. And it's interesting to ask ourselves typically what emerges from this complexity. Is it a robust notion, and can we measure that? And also, also generally, why do we care about this diversity? And are there like fundamental reasons behind that? And I'll focus on two lines of questioning. One, which has to do with this issue at hand, which is when we face an ecological system, it's a complex system of which we don't know much. And so we don't really know how to deal with that. And typically what people do is what I want to call practical reductionism, because I don't want to go in like deep philosophy of what is reductionism and what is holism, but practical reductionism is, for me, is this premise that it will pay out to focus on certain things, even though we don't know many others. And that somehow, like from partial knowledge, we'll be able to build, put the pieces back together and get somewhere. And also, of course, completely related to this question is also dynamical repercussions of complexity, which have been of interest to people. So how do complex communities, complex systems in general respond to perturbations? Can we quantify also how this dynamical complexity, or interconnectedness, this notion that makes this big system be a bit more than just a loose part? That's what I'm going to try to get at. And see if we can reach, at least at an abstract or metaphorical levels, a form of unifying perspective on that. And the methodology that we're going to use is that of networks and dynamics, which comes from somewhere. It's not actually that obvious that it's a good idea to look at ecosystems as networks and then put dynamics on it. But that's what we'll do. So something like that. So there's the network, which is this, like kind of with visually you see its topology, but you want to also put on top of that, on the nodes being species for us. You could think of other ecological entities if you want, but for me I'll always be talking about species. And the dynamics of those nodes are going to be something that has to do with growth rate. So that's why I have the 1/n, the n. I guess there's been like talks about why we put that, and it has something to do with thinking of reproduction as being a fundamental process here. And this empirical observation of exponential growth that is found in many places. So this growth rate of a given node, species, will be a function R of the others. So that's dynamics. And that has something that is somewhat overlaid on this topological structure. So this will be a bit what we'll have in mind, and we'll build something out of that. Okay, so
I'm sorry.
Yep.
The R is like the rate of increasement of nodes.
Yeah.
Okay.
Of the size of the population of that species population.
Okay. But if we're going to conceive the nodes as one species, so it's the whole. It's for all the species of the network. We are modeling communities.
Yes, so if you model a community, you have of S species, you have S equations like this.
Yes.
You
Okay. It's one for each population.
Yeah, and they're in interaction, so they codepend on each other in certain forms. So the classic form is Lotka-Volterra.
Yes.
Okay, so let's go a bit into this notion of like limits of reductionism, or what happened, or indirect effects, or interconnectedness. I don't know which like keywords spark some intuitions in your mind, but you have to think of it a bit like that. And so the problem is really, and it's of course a very old issue, is how you deal with complex systems as whole systems. And in this paper, Levin talks this analysis of partially specified system, which really has to do, for me, with this notion of practical reductionism, is that you want to do something in an ecological system, for instance, pest control, and you have detailed information about how a pesticide affects a given insect species. You know how you've studied the physiology of the response, etc. So you have detailed information there, but you also know that you have a lot of things you don't know, which is who eats those insects in the natural world, what other things are going to be impacted that you don't know, etc. And so when you're going to put in practice your knowledge about the effect of this pesticide, maybe you'll have unforeseen effects in the field, or even maybe completely counterproductive effects, where you'll end up having more pests than before, things like that. And there's this idea that like one-step linear causality, like I do this to that, it will then respond like that. Or maybe two-step causality, if you want to go a bit further. This is typically a poor predictor of ultimate outcomes. Okay, so let's try to get a bit of a picture of what we mean by that. So, of how I'm going to formalize a bit this problem in the rest of the talk. So here, this is a fake. I'm sorry if I'm like being offensive to anyone who knows anything about sourdough or microbial systems. I definitely know nothing, but it's just a small illustration, so hopefully it's not creating confusion. But I wanted to talk about indirect interaction. I want to first talk about what is an interaction between species. And so the way I want you to think about is how the abundance of one species affects the growth rate of another one. And so if you have some idea of that, how the abundance of one species affects the growth rate of another, you can draw a network. Here it will be potentially weighted, so because you don't necessarily make it purely qualitative, you could have strong and weak interaction and so on. So maybe you have a network like that, but now these are in a way direct interaction, and you can imagine that the links that do not exist are because somehow it's a very weak interaction, or you have a cutoff, or whatever, technicalities. But the point is that there definitely exist indirect interactions, because even though some species are not connected, or maybe very weakly, they are connected indirectly by the other. And you can then draw all kinds of pathways like this. potentially an infinite amount of pathways, and you don't necessarily know where to stop. And it is what I'm proposing in this talk is that through this dynamical interconnectedness, or something that I will end up calling collectivity, you can start to, if you can quantify a bit this, you can understand a bit more why systems as whole are really not just like simple assemblages of simple entities or maybe simple interaction motifs. And okay, and this idea that those indirect effects are important, it's something that is, of course, well known in ecological literature, and the classic reference is Yotsis, and there's this idea of like super complicated marine food web, and that is in itself also a simplification of what really is going on. And the point is that even if you had some idea of the interactions there, but only like maybe within an order of magnitude, the outcome of perturbations, like let's say a cull on some fish species, the impact that this will have on another important species, this can be is highly undetermined. So both like who increases or decreases and which interactions end up being important ones and so on. So I don't know why I put this graph, because I don't even know what it means, but I understand this text. All right, so I'm trying to wrap up a bit this long-winded introduction with some like quotes that are a bit philosophical in terms of what should you have in mind when you think of an ecosystem, and from there on we'll try to build a bit this mathematical metaphors that tries to order a bit the ideas that I'm throwing out at you now. So there's a tension a bit of how should you view it. Should you view ecosystems as like really big systems, like even organismic systems? So that's like Clement's view, like, so it's really like there's a notion of succession being like organism development. This notion that maybe a lot of indirect effects have a lot of big importance in whatever happens to communities. And I guess I should have put the counterpart to Clemens, which is I forgot his name. Gleason, yeah, which like kind of like basically contradicts that completely. Says no, it's a stupid way of, or super convoluted way of looking at plant communities. You should see them more as just collection of plant species, independent plant species, like the interaction and complexity, functional complexity is just unhelpful fantasy. But so in his book, Michel Leroy has kind of synthesizes the two. So the two have issues in a way. The individualistic viewpoint fails to take into account the many interactions that bind organism and species together, and which are a bit at the base of what we even think about when we think of ecology, this manifold of interactions and complex interrelationship between cause and effect. But at the same time, the super-organismic viewpoint, so this idea of seeing communities as an organism, also misses, like, or it clearly doesn't capture the lability of communities. Okay, so that was about like how a bit this nature, the nature of those systems and direct effect. But there's another facet of what complexity is that is a bit less philosophical in a way, and tries to be a bit more pragmatic, which is, okay, I don't know maybe what an ecosystem is as a system, but I care about how it will respond to perturbation, how resilient it is, how is complexity and diversity an important thing. And that's a very big, as you probably know and heard millions of times, this is an everlasting debate, because it starts from this observation that maybe some simple communities are more easily perturbed and vulnerable, with some theory that had something to do with entropy at some point. Some other theory of May, which is the exact opposite, which is that actually complex systems should be unstable and not stable, so going completely against like kind of the intuitive viewpoint diversity, stability, maybe also had, that was properly related also to this ideology of balance of nature. And there are also experiments that look at how community stability, so like fluctuations in time of some function or populations, are related to the diversity of the plants, or the number of plants, or the functional diversity of fungi. So, in summary, and you should feel a bit confused because I talked about a lot of things, and I'm just trying to put them a bit back together. When we think of actual ecosystem, we think of long indirect pathways that have a lot of consequences for prediction, and that make even the notion of causality, cause and consequence, rather subtle. This idea that complexity in the dynamics leads to an instability, and yet that experiments and observations suggest something otherwise, or that even that maybe it's not a very well posed question. So what I hope to do is start to use a bit of mathematical abstraction to put a bit of order into this, not solving, of course, but just build like a bit of a metaphorical object that helps us at least see why all those questions can be, at least in principle, related. And what I want to address is how we can quantify the relevant length of indirect interaction, understand the role of network structure in all that, and the signatures of dynamical interconnectedness or complexity or collectivity, and like try to like tease apart those different notions and words. And if we have time, probably we won't, I'll go a bit more into stability ideas and stability metrics, but we'll see. And if we don't have time, that's totally fine.
What's the eternal vigilance?
I guess I was just trying to point back at Seb's talk about using math metaphors to talk about actual ecology, so we should keep, take everything I said with a grain of salt, basically. That I'm not going to come up with, we're not going to come up with a realistic model of ecosystem at all. It just will hopefully give us some intuition, but those intuition we have to also be a bit careful that they come from pretty severe abstraction that might be completely irrelevant. Okay, so now let's go for the formalization, and here I can easily slow down if some things are unclear, and write things on the board if need be, so just feel free to let me know. But just very quickly, the idea would be to start from, as I said, this idea that there's a network, like some growth rate function that maybe like take a bit of this form, like Volterra, and then the central object would be this inverse matrix, which is a matrix that has 1 on the diagonal and some a-dimensional numbers. So it's something like it has 1 plus, and then here this would be the interaction between 2 species. So that's the matrix, and that what I'm going to show is that what matters, what formalizes the idea of ecology in my head is just inverting this as a matrix. And just by doing this very, in a way, elementary mathematical transformation, we get some ideas of ecology. Okay, let's dive in. So, how do we get there? First, we define direct interactions. As I said, direct interactions are the effect of the abundance of a species, so that I write as n, on the growth rate of another. So formally, the interaction between k and j So the impact of J on K is how is this derivative here. And I want to contrast this with the idea of a net interaction or a long-term interaction between two species. And this will be something somewhat symmetrical, which will be rather so if I look at how this species I is impacted in a net sense by species J, it's how its long-term abundance, its let's say a stationary abundance, is affected by variation in the growth rate of species J. And now what I want to do, which is in a way it looks like a small technicality, but it turns out to be a very fundamental step, is to, given all these numbers, so these numbers form, it forms a matrix, right? These numbers, dr, I, I switch a lot between indices. I hope that's not too confusing. So this would be like something let's call it alpha ij. This is the direct interaction between R and J. This has units, has dimensions, like because growth rate could be quantified with some units. Abundance could also be biomass, could be whatever. This alpha matrix is a whole matrix that has numbers potentially a bit everywhere. Maybe it has zeros in some places, but it has numbers a bit everywhere. And in particular, it has numbers on the diagonal, which are what we may call self-regulation. I don't know if you called it that in the previous lectures. Was that the term used, self-regulation?
Yes.
Self-regulation.
It sounds,
What?
it sounds familiar.
Okay. No, because there are other terms for it. Okay, and what am I doing now? What I want to do is factorize these numbers, which may vary across the species. The self-regulation of the different species could be different. I want to factorize that by writing the self-regulation times a matrix that now has ones on the diagonal, and here has so actually I factorize by minus that. I don't know, I'm gonna confuse myself with the minuses. Oh no.
Don't you have any of the correlation?
Yeah.
Because in the end it's
Yeah, maybe there's a blue pen float on the bench that we
But is that clear? Because I can speed up if it's doesn't.
that's good.
Understand that I'm just doing a little manipulation that maybe you don't know where I'm going with it, but it just I want to take out this diagonal, put it in front, so that I am left with a diagonal matrix that I call D, and then something that has -1 on the diagonal, plus a matrix A, and so this has no units. It's numbers. And that's very important. And all the units have been pushed here in D. And that could be an exercise that we can do if some of you are interested later. Is if you think of the net interactions now, so how the long-term abundance are going to change with respect to perturbation of the growth rate of species, you just take this matrix and you invert it. And so if you invert that, So that's a property of matrices. When you invert a product of matrix, it becomes the product of inverses, but in the other way around. So there's a bit of a gymnastic to have in mind when we deal with matrices. So I have something like this. This is still my diagonal matrix, but now it has been flipped. Its elements. This is the matrix inversion I was talking about. And again, this has units. It carries the units of net interactions that are different from the units of the direct interaction. But this has no units.
Question?
Yeah.
So why do you frame it as net interaction?
What was the last word, sir?
I mean,
As net?
So like, why does the long-term effective growth rate on this? Why do you frame it as a net interaction?
Okay. So I frame it as a net interaction because it's the like the direct interactions are something that in a way doesn't let the community dynamics play out. It's just probing immediate effect. Whereas I want to contrast this with how a species will respond to a perturbation of another when you allow all the ecological dynamics to play out. So in that sense, I called it net because experimentally you could imagine that I would make a perturbation of one species and monitor the impact that this has on another in the long run. That would be the net effect.
So the direct interactions are more explicitly assumed, and the net interaction is more phenomenological.
You could say, that. Yeah, you could imagine, for instance, studying the direct interaction in a lab, like isolating two pairwise species, and then look at that. Or you could also, as you said, assume it from mechanistic principles, maybe. Yes. Yeah.
And then just one more, just to be clear, so R and are time dependent?
N are time dependent.
Okay.
At this point, I'm not gonna. I want to build the simplest representation. So I'm not going to assume that interactions are time dependent and so on. But they could be, of course. And state dependent. And there could be many things. And in a way, and you can still do what I'm doing here, but you'll have to include a bit those technical elements of time dependence. But here, let's say that the direct interactions are just some intrinsic, let's call it an intrinsic feature of the pair, which probably doesn't exist. Yes.
Maybe so R. So what is R? Is it like the biomass or like growth rate or?
R is growth rate, yeah.
So like some parameter?
R would be what I would call Ri is dni.
Yes.
I'm sorry. So it's the proportional change in time of the species abundance. And this proportional change in time is a function of the abundance of the others.
That's what I showed on the graph in my lecture.
I have a stupid question. Why is it that A and D is in matrix you want to capture the whole ecosystem or a whole system? Why is it in the matrix is not two species?
More than two species.
Sorry, you're asking?
The A and D is in matrix?
Yeah. This will be like an S by S matrix. S will be the number of species, could be very large.
So the function is about the whole community.
Yeah. I'm building there's a community context, and in this, so another way to put it is that you could imagine, and it's an oversimplification, but you could imagine that the direct interactions are just things, are features of the pairs of species, whereas the net interaction is a feature of the community, of the context. So if the net interaction between two species will not be the same if you remove another one, potentially.
Yes, I maybe one last question. So the matrix D, so the diagonal is like for self-regulation, that's pretty clear. So for the terms, so it would mean the effect of different maybe amount of species J on the rate of K.
Yeah. So sorry, I should have written maybe a specific example so that you would be more. Imagine if I had taken the lot. Yeah, I should have done that. Sorry. If I write the Lotka-Volterra, then I would write dni over dt would be something like some feature like what is it called, the intrinsic growth rate, and then I would put plus like minus the self-regulation of species I. Right, so that is logistic growth, classic logistic growth equation. And then on top of that, I would add the sum of alpha j with j different than I of the this would be in my and in this context, so these are not the same alphas, right? Sorry, like choosing alpha here, we're gonna use alpha later. That's for notation. Notation, yeah. Notation is Aij here will be the alpha ij divided by di. So that ratio. So now it has the units. And yeah. Is that okay?
Yeah.
A question just in order to
It's fine.
checking if I'm understanding. So by this approach, you don't, in the matrix, you don't have zeros.
You might have zeros.
You might not.
Not on the diagonal. Is that what you mean?
No, at the whole, because you always will obtain a number if you, for any indirect, if the matrix is connected, if all the species are connected.
Ah, you mean the invert? Once I invert the matrix, I don't have zeros anymore. Is that what you say?
No.
Yeah. Well, this number could be zero. There could be species that are not related, but the way I understood what you said is that when I'm now going to look at the inverse matrix, then this thing ij is probably never going to be exactly zero, because there's always going to be a way, even a very weak, even in a very weak sense, there's going to be somewhat of an impact of one species on another.
Because each a number on the matrix is given by that formula, dni.
Yeah, so this this expression would be the general definition I would use of an interaction. But in Lotka-Volterra, it's immediately a parameter. It's just this. It's called alpha.
The suggestion maybe to illustrate what is d and star over the r. When you just have the logistic, you know that the equilibrium abundance is just r over self-regulation, right?
Yeah.
So maybe that could be.
If you had no interaction part, then you'd have that ni star is r over d I. And so you see that the net effect of species on itself is one is and the direct effect of species on itself is d or minus d. So you go from minus d to 1 over d, which is, that's why you have like this in the generalization, you have the minus and then inverse, which takes this particular form here. Okay. Is that all right? So why am I doing this? I'm doing this because I like, because this subject, it turns out to be quite nice to study. Because it has a very simple infinite series expansion of this kind. And in this infinite series expansion, which has a convergence radius, we can now recognize and meaningfully talk about indirect effects. Because I talked about indirect effect before, they are a very intuitive notion. You say, oh, an indirect effect is when I affect that entity that itself affects another, and so I'm indirectly. But to formalize it mathematically for me, requires to go through this step. Okay, so why am I writing it like this? So this series of writing this matrix like this is just the matrix version of this very simple formula. So is everyone okay with that? Or?
I can't really remember you defining the A matrix. So A is a matrix, right?
Yeah.
So what is it?
It's the ratio of interactions, direct interaction over self-regulation, self-interaction. So it's a ratio of, and the point is that, as we will see, the strength of the direct interaction per se is not what matters. It's the ratio of this strength and the self-regulation.
Maybe we use another notation in our lectures, which was just Aij over Aii. And I don't know if that helps or not. It's the same as what I showed and Arno showed also.
So is there an assumption on this ratio, like you can easily go from 0 to infinity, right?
Yeah. Yeah, the only annoying part would be if the denominator would actually be 0, and I'm going to assume that it's not.
Just the identity at the top, is it valid for any matrices? Because here it's for x.
Yeah, that's right. I was going to say.
Sorry?
That's the convergence radius.
Okay.
But yeah, you're right. The point that you're making is that I can write this. So this is just for numbers, and this is not matrix. It's just 1 over 1 minus x. I can write this as 1 plus x squared and keep going. And this series converges to the right answer only and as long as the absolute value of x is smaller than 1. If the absolute value of x is larger than 1, this series blows up, whereas this thing doesn't necessarily blow up. This thing is well defined, except at x precisely 1, but anywhere else it's fine. Whereas this thing, as soon as x is larger than 1, becomes meaningless. And I want to use this intuition also for indirect effects. So I try to give like an ecological intuitions around this idea. The point here is that we recognize here the direct interaction between species without in terms of this ratio. And when we have the square, we see that as indirect interaction of order 2. So the interaction that goes through one node before coming back, or before reaching its target. And more generally, when you go up to order k, it's the indirect interaction of order length k.
I wonder if you could actually explicitly write the element ij of matrix of a square maybe as a
Sorry, my throat is itchy. So if I look at, I'm going to make a little drawing. So order 1 is just Aij, but order 2, what is this? This is the matrix product of A 2 times. So it's the sum over another index that I'm going to call K, of A, I, K, A, K, K, Kj. So that's the matrix product. How do I interpret this? Well, I'm going to draw, so these are my targets. So this is the impactor, if you want, and that's the impacted. Oh, yeah. So let's write this as a node J, and here I'm going to copy, in a way, all the nodes that actually have a link to J and I. And this is my list of Ks. And here is the target, the impacted. So there's what the second order indirect interaction term means is just this sum. The sum over, I have this interaction, I multiply this number by this number, plus this number by this number, plus this number by this number, plus, etc. So I'm summing all the interaction pathways of length 2 that connect species J to species I.
You do that for 4 clockwise interaction with species.
Well, this gives me the element A square ij, and then I fill in my whole matrix by doing it for all.
I've been told that it's wrong to consider that order 2 or order K can be interpreted as time steps, but I don't remember why it's wrong.
Can I not go there right now? I don't want to go there now.
Okay.
I'm afraid it will be very confusing. But you are right that okay. Yeah, let's try to keep it simple at this point. All right, so there's a.
I need some kind of clarification because what we seen in the previous slides.
Slides?
Yes. It was the net interaction. Yes, cool.
Yep.
Okay. For me, it's an indirect interaction, or why not? For example, if the red one that goes from G to I, it's not an indirect.
Oh yeah. Okay. So the point that this series is making is that the net interaction, so this thing, should be seen as the sum of all the indirect interactions.
Okay.
So that's why that's really the only reason why I'm using this notion of net interaction is just to make appear the idea of indirect interaction in a meaningful way.
Okay.
You also have the direct interaction. Okay, it's direct plus indirect.
Yeah. So yeah, this is direct, indirect of order 2, and so on and so on and so on.
At the end, you are going to find a matrix that resumes all the direct and indirect.
Yes, exactly. That is this matrix.
Okay, because two species may have a direct interaction, but also there are another path between them, indirect path between that pair, and you account in the whole value.
I'll give an example of that. Yeah. Okay. Even if you have just 2 nodes, you can still define long loops. Like I'm not necessarily interested in interaction pathways that never loop back on the same node. I can go around forever on it, between 2 if I want. And so what's very important here is
just for clarification. So X here is so
X is the ratio of alpha over di, right? And
X, sorry, what? A.
no, X.
X is just an example here.
Yeah, but we understand quickly that it has to be below 1, otherwise when you multiply your I chi over A G, if they are above 1, then they will explode. I mean,
right.
And further, like the two steps interactions, they will be larger than the direct one, and the more you increase your indirect interactions, the stronger they will be as soon as this ratio is above 1. So we are, in comparison to the lecture of yesterday, in a regime where self-regulation has to be more important than A, so the interaction. So we are, correct me if I'm wrong, but we are in the regime where we don't have like this super strong feedbacks, and you have the lambda that is like closer to low values. I mean, we are in the diagonal of like 5 even at the maybe, but we are in the regime of the static world where everybody is self-controlling itself, and we are not in the mutual control.
I mean, the point is that to even start writing this, you need two species to be in a, I mean, at the two species level, you will need to have interaction not too strong. But it doesn't mean that with many species, you will still not be too strong. That's correct.
Yeah, so you're right that if it seemed when I write it like this, if I just forget the sum, I have a product. So if the product of these numbers is greater than, if each term is greater than 1, the product is greater than the individual value, so it starts to grow. But it can grow for another reason, which that there is as the order grows, the number of pathways also grows very quickly. So even if all these numbers are small, it can still blow up. Sorry, maybe I'm not answering your question super well, but maybe in a sense you're right that to start writing things this way, you are in a regime where things are quite well regulated, and they will quickly stop being well regulated. And yes, okay. So the criteria for writing this series, for the series to converge, is determined by what's called a spectral radius. So does everyone know about eigenvalues of matrices? Is that a notion that is okay? Okay. The spectral radius is just the largest eigenvalue in modulus. So it's not the largest real part or the largest imaginary part, it's the largest imaginary modulus. Okay. And the reason why it's something a bit more complicated than just having the values greater than 1, smaller than 1, is precisely because you have this sum, this thing here that might explode even though the individual terms are small.
But being strictly below 1 is a necessary condition, or for each coefficient, or not?
Good question. You mean that if just one of them somewhere is larger than 1?
That's my question.
I don't want to answer, because I might say something wrong, but my intuition is that no, but maybe yes.
So if you have negative coefficients, it should be able to cancel out.
Yeah.
But if all of them are positive, I think you have at least in your sum the value itself, and then
that's the Perron probability.
probably.
I don't know. Yeah, but I guess I haven't thought about it too much this way because I was thinking of it more in the other way around. That even though they are small, you can still have something that grows, which is a bit the point is that when you have many species, even though all interactions are weak, the fact that you have many can start to have a lot of weight given to those interact pathways. Okay, how am I doing with time? Probably very badly. Oh, Jesus. Okay, so we're definitely not going the whole way. That's good. Good news. So the point of this construction is that I want to use this abstract value, the spectral radius, which tells me whether or not I can. Actually, it gives me something a bit more. Sorry. I want to call this value the collectivity parameter. So I want to make this point. I want to propose that looking at this number is a way to quantify a bit this dynamical interconnectedness of communities, at least in an abstract sense. Why am I saying that? So if to give you this the intuition, it's something if the parameter is small, then it means that the net interaction between two species is essentially just the direct interaction. So if you want to know what's the long-term effect of one species on another, it's the same as the short-term or direct effect. It's there's nothing too complicated and community-wide going on. But as the collectivity parameter grows, the number of indirect paths, the order of indirect pathways that start to actually contribute grows very quickly and actually diverges when you reach 1. So when you reach 1, it doesn't mean that the community explodes, that there's necessarily some crazy things happening. But as you will see, typically there's counterintuitive things happening. But what we can say for sure is that if you are beyond this value, it doesn't make any sense anymore to think of the net effect between two species as a sum of, like, you can't just add this idea of doing this stepwise causality. That doesn't work anymore. You can't say, I'm affecting this, that is then affecting that is then doing this, and then, okay, I start to keep track of a lot, and it maybe becomes confusing, but it's not just confusing, it's just wrong. It doesn't even work.
If I can just say a quick word, during the feedback lecture, Leo had actually presented this question of when can't you just ask, okay, which feedback is the important one, and just focus on this one, and that's exactly the answer to that question. When you're in this collective regime, you cannot do this decomposition.
Right.
So does that mean that there's some kind of interaction? So
yeah, the whole community is.
Yeah. So let's see what's some signatures of that. Okay. So that I created a bit this abstract construct, but it's what does that matter? So we can revisit a simple food web example, or even just predator-prey, like very simple. And write it, I don't know if you wrote it this way in the lectures, but you have the growth rate of the predator, so it eats the prey, has some self-regulation, there's a trophic efficiency, and the predator, and then, sorry, that's the, oh no, sorry, my bad, typo. So this is the growth rate of the prey. The prey has maybe some positive growth, is eaten by the predator, and has some self-regulation. We can work out this exercise and calculate the collectivity parameter, and find that it's proportional to the attack rate. And if you followed the previous part, it would be probably not just attack rate, but attack rate over self-regulation. But for what I'm trying to illustrate now, think of the attack rate. And if I then look at the net, I'm going to plot here the net effect that the predator has on the prey as a function of this collectivity parameter, which is, you can think of it as me varying just the attack rate. So increasing attack rate, I increase the collectivity parameter, and I look at the net predator-prey interaction. So at first, this net effect, this net predator-prey interaction, it grows. Attack rate increases, the net effect between predator and prey increases. And then it plateaus exactly as we reach collectivity equals 1, and then it starts to decay. So we now have this counterintuitive phenomenon. I don't know if it's a real phenomenon in nature, by the way. It's just a mathematical thing. That the net effect between predator and prey decreases as you increase attack rate. Did everyone understand? Is that okay? Because there's something deeply confusing about that. Like it doesn't sound right that if the predator attacks more, that has less and less of an effect in the long term. And why it's confusing is that it doesn't make, you cannot explain this decay by starting to add up direct then indirect, because in this phase, this is precisely where you cannot sum. So the fact that it's decaying like this is something that is not explained by just like stepwise causality. Another, maybe a little bit more intuitive signature is that so here it's based on simulations. Imagine I take, in my community, I remove one species, there's an extinction, and this species is connected only just to a few interacting partners, and I wonder how far the repercussion of removing a species is having into the network. And that's a bit, so as I said, this is a bit more intuitive. The more, as you increase this collectivity parameter, the depth of the perturbation grows. You also recover this notion of a form of unpredictability in the sense that there's a potential very strong discrepancy between what you would see in the short term and what actually happens in the long term. So here I imagine an ecosystem and there's a change, some permanent change in environmental conditions. And I monitor the species response to this change in the short term, and I extrapolate. So, sorry, here would be low collectivity. I extrapolate, and my extrapolation matches what the long-term dynamics gives. But in another more high collectivity, with high collectivity, the short-term extrapolation is quite unrelated to the long-term effect. You even have like a flip in the trends. So species start to decline and then they grow back up. Some of them. I'm not showing all of them. Also, as you increase this collectivity parameter, how monocultures explain polycultures start to weaken. So you have the abundance in monoculture and the abundance in polyculture. When there's low collectivity or interconnectedness, the two are strongly correlated. But in high collectivity, not anymore. Like some species have high abundance that they would not have in monoculture and so on. However, what does explain the abundance of the species is by forgetting completely the monoculture information and thinking of kind of the species as all, in terms of their monoculture growth, equivalent, and they are differentiated just by how they feel the net interaction with others. So the way the communities, the abundance distribution is shaped is really interaction driven.
Question. So are these like simulated based on the Lockyer return model?
Yep.
And then like, can I understand this as like increased collectivity means like a more multi-species correlations or like something like that?
Well, I don't know. I guess I'm running out of time, but okay. Let's try to. In the next slide, I will try to explain what drives this collectivity concretely. Okay, and see that it has to do with obviously interaction strength, but there's also a contribution of interaction structure and so on. So here I'll skip that. That's just, for those who know matrix norms, you can do a little manipulation of the matrix norm. And what is interesting is that you can find that the collectivity parameter is bounded by a certain notion that is called the Frobenius norm, and which turns out to be something that it's a statistic of the interaction strength, and it's precisely what Robert May called complexity. And by doing a little manipulation, you can find that collectivity, so my parameter phi, is roughly bounded between two values. It's greater than May's complexity measure, and smaller than complexity measure times square root of S. In Gim's talk, there was like the May's complexity that occurred. But for me, I don't really see that as complex. I mean, it's a bit annoying to call it complexity because it's in a way, it's just interaction strength. But, and however, this part here, the lower part, is the equivalence between C and phi happens when you are in a random case, in a completely random interaction case. So it means that complexity in May's sense is collectivity in the absence of structure. Right. So that's just to show this equivalence relation on a graph, and complexity in May's sense is something that has to do with the number of species, the strength of realized pairwise interaction, and the connectance of the network. And so it's really a basic network statistic that gives you the bound of collectivity. And why is that useful? Well, first it tells us what drives, like in a way the most basic driver of this collectivity, so interaction strengths and number of species. So that was answering your question. But you can also quantify the role of network structure by asking yourself, where do I position myself between those bounds? Knowing that if I'm at 0, it's like a random structure. If I'm at 1 now, I just did a renormalization so that at 1 I'm at the upper bound, at 0 I'm random, and negative values means that the structure the non-random structure is making the system less interconnected than it should be, in a way. So let's see an example of that. Here's an example of a food web, where the topology is drawn from like the cascade model, for those who know. It's just the idea that you have like high predators can eat a bit from anything below them with some probability, and then I draw the interaction strengths at with some random value and so on. I mean, it doesn't really matter. But the point is that I'm going to vary the trophic efficiency. So how much gain do predators have from with respect to how many biomass they take away from prey. And here I'm looking at, I'm drawing this here, and the blue value tells me the position between the bounds, so 100% or 0%. And so what we see is that at very low trophic efficiency, I'm less interconnected than I should be, whereas at high trophic efficiency, I'm very high. So how do you understand this? Well, at low trophic efficiency, it's like the system, the interaction becomes very nested, because there is, in a way, high predators affect a lot of people, but they don't really gain anything from what they're doing. So it becomes like a nested system that completely buffers feedback loops. So nested structure buffers feedback loops, and then in the end, when you have high trophic efficiency, you actually have high collectivity, and then the dashed line would be what I would have predicted if I used well, sorry, let's forget about that. This is just like prediction from random matrix theory, just to show that it's not at all behaving like a random matrix. So it's really like a structural effect. And yeah, this is an illustration just to show like a proof of concept that the collectivity is then therefore controlled by basic interaction strength statistics and network structure. So there's oftentimes we can imagine finding the particular interaction structure and the network and the statistics of interaction strengths that determine this collectivity. So I'm going to try to wrap up because we're running out of time. But this slide was just to reconnect with local stability in May's sense. And May was looking at how in a way, how not the spectral radius, but the dominant real part was growing with a complexity. And from what in his paper, he was pointing out that instability grows with his notion of complexity. But what we find ourselves is that, well, it's true for completely random matrix, all those notions are equivalent, like the interconnectedness, the collectivity, complexity, and instability, they go hand in hand. But in general, in the presence of additional structure of whatever form, it's no longer necessarily true. You can have instability typically requires a high, it's a form of collective outcome, a highly collective outcome that generates unstable behavior, like chaotic behavior. So you need the high collectivity to be unstable, but the converse is not true. You can have high collectivity without being unstable. And because whatever the network structure, we always have that complexity bounds collectivity, we end up with this realization that somehow May's result was that complexity begets instability, but he was using random matrix. Whereas here we have an explicit relationship between collectivity and complexity that doesn't rely on random matrix theory. So in a way, I would say that complexity begets collectivity is a more general statement than complexity begets instability. So let's do a quick summary. So what I showed you is that this made this math metaphor of transforming this problem of complex communities and the problem of seeing systems as wholes or collection of loose parts into like this simple, well, this is the spectral analysis of a matrix, and from where we understood something to do with indirect interactions, and that was part of what Levins was talking in his paper about underdetermined systems. Stability, as made by connected to complexity, sensitivity like in unpredictability as Yotsis, and we were able to talk about the role of structure as being a deviation from May's complexity method. So I'll stop here just with reminding that I think for me this work is useful to organize my thoughts and give myself some intuition, but nowhere did I put anything actually realistic about ecosystem. I didn't talk about space or meta-community or dispersed. There's so many billion ingredients that are not there that it's not necessarily easy to know how far you can take those conclusions, but it just helps a bit to see why already in principle the notion of stepwise causality when you're looking at a complex system is problematic, and how but you can go a bit beyond just saying it's problematic. You can have some idea of where you are for a given system if you can access this notion. Yeah, thanks. Questions?
Yeah, I still look at like what's the difference between collectivity and some like a stability criteria that may be.
Oh, so in a way it's a very, well, okay, so I'll go back. It's true I went fast on that slide. So this would be the difference. That if you looked at a Lotka Volterra that had a steady state, you would, so that would be the steady state and star, and you would like to know how do near equilibrium dynamics behave. You would write the Jacobian matrix J, and so small, sorry, that's a typo, there should be no D here. But the point is that deviations from equilibrium behave as exponential, an exponential matrix applied to the initial condition. And so if this exponential grows, then you have instability, like a tiny perturbation grows. And that's the criteria for stability, is that you should always have exponential decay. And in terms of eigenvalues, it's the dominant real part of the eigenvalues of J should be negative. So here, for instance, you have in blue 10 species random community, and the dominant eigenvalue is negative. So this is a stable, would be a stable matrix. Whereas in orange, it goes beyond, it's unstable. The difference between collectivity, there are two differences. First, one difference is that actually it's the eigenvalues of J that you should be looking at, which has the diagonal in it. But that's somewhat more of a small technicality, because in a way you can, at first approximation, you can think, well, this is just proportional. And so if this part here is stable, then this one will be stable. It's not exactly true, but it's likely true. So this means that I can still focus on my matrix A to talk both about stability and collectivity. And there, now the difference is just, am I looking at the real part or the spectral radius, which is just the largest size of eigenvalues. In some cases, for instance, in the predator-prey system, in predator-prey systems, or if you have completely anti-symmetric, so this is A. My instability will be here. And for certain systems, you have the eigenvalues are completely imaginary. So they are like here. So they can grow very high in terms of the spectral radius. In terms of stability, it seems there's no effect. So it's for random matrix, because eigenvalues grow as kind of are within a circle, the largest radius and the largest real part is the same thing. That's why in the random case, there's no distinction. But as soon as you have like a spectral radius that has a different shape or whatever, then it becomes a distinction.
So the collectivity considers the shape of these clusters, but the stability criteria doesn't care about it. Does that make sense?
Yeah, the stability criteria only cares about the real part.
Yeah.
And whereas the collectivity cares a bit of both. But it's still kind of agnostic to a lot of details.
Can you go back to the slide where you gave the simple predator-prey model and you show that you get that counterintuitive example?
This one?
Yeah, I guess I'm still struggling how we're supposed to interpret collectivity past one. Like, why does the counterintuitive phenomenon pop up?
Why?
Yeah.
Well, how do I answer it? I think the way I can answer is that if I was before one,
Yeah.
then there would be no way you would imagine this behavior, because here I'm increasing the attack rate, and I'm looking at how the predator impacts the prey. So I can say, well, it impacts it directly by attacking it. But then I can look at, so I can look at all the orders, you see. Imagine I have my predator and my prey. So you have attack rate like this, and then you go back as epsilon attack rate, to simplify. So I have, how do I impact this when I go A? I attack the prey. But then I say, well, you know, the net interaction, you have to sum. You have to sum all indirect pathways. So what's the next one? The next one is that I go A, so there's a minus. I go, no, this one is positive, this one is negative. Minus A, and I go minus A epsilon A, so that's epsilon A squared, and then minus A again, so it will be minus epsilon A cubed. And then I keep going like this. Okay. And you see that there's no way, like if this thing converges, there's no way it's gonna decay as A grows. Because there's just this moment where there's a point where the net effect cannot be understood like that anymore. It just doesn't work. And in this particular example, the fact that it doesn't work is made evident by the fact that we have this phenomenon of a decay of net interaction with data rate, which is specific to just this predator-prey system. It's not like I'm not claiming that in a general food web the net effect between a given prey and its predator starts to decrease.
Right.
It's just here you have this particular phenomenon that, for me, illustrates the impossibility to decompose net effect directly.
In this setting, don't you get a breath for the term with the A cube? Because you get 2 minus. And then what should be the...
Yes, it's a plus. Yeah, it becomes an alternative sum, that you don't necessarily know which way it's going to go.
Yeah, and so is there an intuition behind that?
You mean why it's positive?
Yeah.
Why is it positive? Well, I guess it's because you are depleting your... So, you know, by eating your prey, you gain something because you're eating it, but you're also depleting your resource, which itself is a good thing for the prey. And then you go to the next step, and then it reverses, and then...
I see.
You see?
One potential problem associated to the scalability criteria is that maybe the system is stable because of a limited number of unimportant species, but if you remove them, then the system can become stable.
Yeah.
From this point of view, does the collectivity parameter circumvent this problem?
Yeah, because, that's a good point. That has to do a bit more with the ton of stuff I was thinking I was going to talk about, that I'm not talking about, which is that I mentioned here that stability here has D in it, and this D here contains abundance of species typically. And so when you have very rare species, they're going, because you're multiplying by a very small number, you tend to have an eigenvalue very close to 0. So like something that is showing instability, and this instability is related to the fact that one species is close to extinction. But that problem is not present in collectivity, because you don't have that abundance of effects.
It also means that D is not in collectivity, which means that the intrinsic growth rates of the Lotharia are not in the collectivity.
Yeah.
So this is all depending on just interaction parameters.
Yeah. For,
Not surprising.
but not for lot Cavolterra, because in lot Cavolterra the interactions are like direct parameters. But if you had written a different model with some functional response and so on, then then you would intertwine all parameters. But of course, a lot of what I did here relies on uses the assumption that I have a steady state, that it makes sense to have a steady state. That's a big limitation in terms of. I mean, I think a lot of the intuitions remain, but I don't know how to translate directly into like non-equilibrium dynamics. But the intuition for me is like they have to still stand, you know. But I don't know. Okay.
Just break it. Can you use this notion of collectivity and like first order, second order interactions to say something about the transient dynamics and like the short-term response to a perturbation, and does the like second order interaction can tell you about like not the first response but the second response? It's just an intuition.
I'm going too far with this. Okay, no, I think you are asking what Seb was asking before, which I can. I mean, people who want to go have lunch, go ahead. But it's okay. It's not that hard. It's that if you now think of a linear system. So don't look at the slide because that's just going to be confusing. As I said, you have that the local dynamics is going to take the form of exponential times Jacobian times the initial condition, like this. That's linear dynamics. So it's the solution of dx over dt equals jx, right? With the initial condition like 0. So exponential has should I do it like this? Okay, I'm going to do it like this, but I think there's a better way. But exponential, I can write it as 1 plus tj plus t squared over 2j squared. So I see here, by writing it in this form, I see that through time you'll have higher orders that are going to become important, which are not at small times, because at small times this t squared will take over and collapse everything. But really short times, I just have this directed, and J, remember, is kind of proportional to my interaction matrix. So at first, at short times, I just have direct interactions, then at a bit longer times, order 2, and so on.
The small is below 1.
Well, it depends on J. If J is very small too.
So then, what I said earlier is partly incorrect, but not totally.
What you said earlier.
Can you repeat what you said earlier?
There was this idea that the exponent of the interaction matrix can be interpreted as the number of times that you. And I remember that this intuition is incorrect, but then when I see the development you make of your exponential, I'm not sure that's incorrect.
it's not so easy because you see J is this, so if I have, yeah, it's not, if I had literally this, then that would be completely correct, right? Via time, you just have indirect interaction of longer orders. But I don't have A, I have J, and J is this. And so when I put this to the power K, I have this to the power K, so now I have to develop this to the power K, and I have different orders in that. You know what I mean? Like it's a bit more messy than, so.
Okay, so that's the mathematical reason.
Yeah.
Given intuition.
Yeah. Yeah, it doesn't map so well with the intuition. It just tells you, yes, time allows indirect effect to take place, but it's not as simple as just.
Isn't the intuition that over time you have more and more indirect interaction, that the one at lower orders still play a role?
Yeah.
Somehow that's.
Yeah. But I had another way of putting it that I don't know if you're gonna like, which that for me was so there's too much details here, but what I was going with this is imagine that instead of doing a of looking at the net effect by saying I'm affecting the growth rate of a species and I'm looking in the long term what happens to someone else, I'm imagining I have some noise. I do a perturbation of the system at several frequencies. So I have like oscillations of the climate over long time scales, maybe oscillations at short time scales. Okay, this would be my frequency omega. And if you do a Fourier analysis, you end up finding something that is kind of nice, is that you still recognize this kind of, so this would be the response to this oscillating perturbation. And what you find is that you still have this term that we saw, like 1 minus A inverted, but the A in here depends on the frequency. And if you look at how it depends in a way that tends to decrease with frequency. So high frequency is short time scale. So short time scale means that the effective interaction is weak, so you don't have collective phenomenon if things are over two short time scales. But it's only over long time scale that you might. So you can, via this reasoning, you see that time scale can probe different degree of collectivity. Okay, that was, I'm sure, too technical. Okay?
Can we just fast forward to the last 6?
Here I was showing that depending on perturbations, you see different stability patterns. And depending on observation, you also see different stability patterns. So for me, it was this idea that you have, I was pushing this notion that has been part of it of my research, where for instance, stability is not a super well-defined notion. You can think more of perturbations. They probe different behavior. And those behavior can be collective, not collective, can show increase with diversity or decrease with diversity. It's more like where I was going with that.
Did you publish this one, this figure?
No. I used it to get a job and then I dropped it. It's true. Okay. Yeah, I think everyone would like to eat that. I don't want to, I feel like I'm holding people.
Before everybody discusses, can I make an observation of people going canyoning? So Leo, you are. Mariana, you are. Ming, you said you're not. You're not going canyoning?
No.
Okay. Dina, you are. You are. Okay. Stephen, you are. No, you're not. Okay. Federico?
Yes.
Yes, you are. Arnaud? Yes. Okay, perfect. Then today's game would be Leo, Mariana, Ming, and Vivian. Wait, yeah,
I have this question for you. I don't have to show you questions on like all the keepers just to be clear. So if INTP is like a hard just like that, so one of the problems that we use is sometimes it's just an umbrella term, like